Different types of noise functions produce different types of results. In the last video, we went over value noise, which is a type of smooth noise that is commonly used to generate infinitely procedural terrain, like in Minecraft or No Man's Sky. In this video, we'll go over Worley or Voronoi noise. This type of noise is useful for generating organic cell-like structures that you might see in nature, like the wings of a dragonfly, the cells on a leaf, or the patterns on a giraffe. It's also the basis for generating realistic clouds, as you may have seen in video games like Horizon Forbidden West. Needless to say, Voronoi noise is a very useful technique to add to your shader toolkit. Let's jump straight into the algorithm. In order to create Voronoi noise, we start by creating a grid of cells. In each grid cell, we can add a point at the center. Then, we iterate through each pixel and find the minimum distance to the closest point. In this case, it's easy to see visually that any pixel will find its nearest point in its current grid cell. Plotting the distance to the point will produce an evenly distributed result, as you see on the right here. To make this feel more organic, we can offset the points in each grid using noise, like so. Notice that by adding noise, we also increase the number of checks we need to perform in the algorithm. This time, each pixel will need to check for the closest point in its current grid cell, as well as the 8 grid cells adjacent to it. The resulting shader looks more organic, and you can see it here on the right. I've kept the red lines in here just for reference, but we can remove them later. And finally, we can invert the shader in one line of code to make it look like clouds. As with all of the shader tutorials, we're going to set up our UV coordinates, which go from 0 to 1 on the x-axis and 0 to 1 on the y-axis. We're also going to set up our color variable, which is currently 0, which is why the right screen over here is completely black. If I were to set this to 1, you'll see that it turns to white. Now, the first part of the shader is to set up the grid, and that's what we're doing right here. This is an easy way to get the grid coordinates. This goes from 0 to 4. But taking the fract of that will ensure that we go from 0 to 1, 0 to 1, 0 to 1, 0 to 1, 4 times. So if I were to color this, you'll see that that's exactly what we get here in both the X and the Y axis. Now, one thing that's going to be helpful for us is to center this at the center of each grid cell. So that's what I'm going to do here. And essentially, that's just going to give us something that looks like this. The next thing is to draw that red grid. You can pause and take a look at the math if you really want to, but essentially what we're going to get with this formula is the distance to the edge of the grid cell. So if I were to plot this, you'll see that obviously at the center it should be 0, and as it gets closer to the edge it should be 1. And if we were to add a smooth step from 0.5 to 1 based on the distance to the edge of the grid cell, then you'll see that it starts looking more and more like a graph. Playing around with the values, I've found that this works the best, and I've only set this to be the red color. So if I were to save that, you'll see that we get our red grid cell. So now what we're going to focus on is adding this grid with these center points. For each point, we're going to check the 9 adjacent grids. For example, if we were checking some point over here, we're going to go from -1 to 1. These 3 adjacent grids, these 3, and then these 3. So essentially, that's what this loop is going. And in this loop, what we want to do is get the point on the adjacent grid. Right now, I am saying that the adjacent grid point is essentially just at the center. And what we want to do is get the distance from the current point to the point on any of these adjacent grids. We can take the minimum of those 9. An easy way to display what's happening is I'm going to display the red grid, I'm going to display the point on the grid, and I'm going to display the minimum distance from the pixel. And if I save that, you'll see that we get our basic Voronoi shader. Suppose the pixel that we're trying to color is right here. Eventually it's going to go through all of them, and it's going to keep track of the minimum distance to any point, which is this point right here. The distance from here to here is a very small distance, and what we're doing here is coloring based on the distance. So if the distance is essentially 0, then we would expect it to be completely black. Now, obviously you're not seeing that because I'm displaying the point, but if I were to remove the point over here from the color, you'll see that at the center it's completely black. And on the edge, if I remove the red grid color, you're going to notice that at the edges it's almost white. The only reason I had the point and the red grid was just to sort of make it clear visually what's going on. Now let's take a step further and randomize the points. What I'm going to say here is that the point on the adjacent grid is based on the sine of the time variable multiplied by 0.5. And if I save that, you'll see here that the points go from 0 to 1 and then to -1. But because we're multiplying by 0.5, it's only going to the edge of the grid and not to the next grid itself. That's not really that interesting. So let's create a noise function and pass in the current grid ID as well as the adjacent chord. So this noise2x2 function just sort of takes in a vec2 and returns a random vec2. This is just a pretty straightforward noise function. So let's go back here. And this time around, let's say that the point on the adjacent grid is based on the sine of the time multiplied by the noise, and see what happens. And there you have it. So now you have points moving sort of randomly. You can sort of see that everything is handled straight out of the box. Now all that's left to do is to figure out how to make the clouds. As I mentioned earlier, it's just as simple as taking 1 minus the minimum distance from the pixel. So it's a very quick change. So if I were to save this, you'll see that we get clouds. And yeah, that's going to be it for today. Hopefully now you guys have a better understanding of how Worley or Voronoi noise works. If you've made it this far, I'd really appreciate it if you could just hit the like button and consider subscribing for more videos just like this. Thanks for watching, and I'll catch you guys next time.